In this presentation, I am going to explain dynamics of motor load systems. Coming to dynamics of motor load system, this is representing a motor load system. A motor is that is coupled to a load, and a motor generally drives a load through some transmission system. Through some transmission system, motor is driving a load. Now, while motor always rotates, the load may rotate or may undergo the translation motion. But always the motor will be rotating, but the load can be either it will be in the rotation, or in certain case there will be linear motion is also the translation motion also there. That is decided by the method of coupling between the motor and the load. Therefore, motor load system can be represented by an equivalent rotational system as shown above. Therefore, motor load system is represented by like this one, in which the motor torque is represented here, and always the load torque will be opposite to the motor torque. It is in a anti-clockwise direction, in a clockwise direction, and the load torque is in anti-clockwise direction, and in a clockwise direction the omega m is the J is the moment of inertia of the motor load system referred to the motor shaft, that is in kilogram meter square, and omega m is the instantaneous value of the angular velocity of the shaft in radians per second. T is the instantaneous value of the torque developed by the motor in Newton meter, that is capital T, and TL represents the instantaneous value of the load torque referred to the motor shaft in Newton meter. That's actually T small l, is not small l. For a drive with a constant inertia, we'll be deriving the equation. Anyway, the relation between the torque of the motor and the load is equal to the motor torque is equal to the torque developed by the electromagnetic torque developed by the motor equal to load torque plus J is the amount of inertia J into d omega m by dt. This is the motor load system having the moment of inertia J, and the product J into omega m is called angular momentum, and torque can be defined as rate of change of angular momentum, or it is called d by dt of J omega m. Therefore, the net torque here, the motor torque minus the load torque, T minus TL, that is equal to d by dt of angular moment J omega m, or that is equal to J into d omega m by dt plus omega m into dj by dt. What we are assuming is that J is a constant, that is the drive is having a constant inertia, therefore dj by dt equal to 0. Therefore, this equation now it becomes T minus TL, that is actually the difference in torque, that is the accelerating torque, T minus TL equal to J into d omega m by dt, where J into d omega m by dt also called dynamic torque, and it is present only during the transient operation, either during the starting or during the acceleration or during the braking or during the deceleration. During that period only this component J d omega m by dt will be present. Therefore, T minus TL equal to J into d omega m by dt, or the electromagnetic torque developed by the motor equal to the load torque TL plus J into d omega m by dt. Continuing the dynamics of motor load system, T equal to the electromagnetic torque developed by the motor equal to the load torque TL plus J into d omega m by dt. Now, if T is more than TL, if the load torque of the motor, electromagnetic torque produced by the motor is more than the load torque demanded, or the torque demanded by the load, then we can say as per this equation, if T is more than TL, d omega m by dt will become positive, meaning that indicates the drive is accelerating. Hence, drive accelerates. If T is more than TL, drive accelerates. If T is less than TL, if the electromagnetic torque developed by the motor is less than the motor torque, then d omega m by dt is equal to negative. Hence, meaning that the drive is decelerating. Or if T equal to TL, if the electromagnetic torque developed by the motor is equal to the torque demanded by the load, T equal to TL, then d omega m by dt equal to 0. that is called drive is that case we call drive is stationary. Therefore, energy associated with dynamic torque, that is called J into d omega m by dt, is stored in the form of kinetic energy half J omega m square. Therefore, this is the equation, dynamic equation relating the motor torque, load torque, and the speed of the motor, moment of inertia, etc. Previous slides we have seen the torque produced by the motor T equal to TL plus J d omega m by dt. Or now let us see what are the different components of the load torque TL. Different components can be broadly classified as three components. One we call it as friction torque, second we call it as windage torque, third is called the load torque TL. This is the torque that is producing the mechanical movement. Therefore, these are three components are there for this TL. Now in this one, let us see first one, friction torque. The friction torque, friction will be present at the motor shaft and also in various parts of the load. And friction torque can be resolved into three components. Again, friction torque has got three components. Now this is showing the friction torque of this one. That is friction torque versus omega m. Torque versus speed. Characteristics of a friction torque. Tf versus omega m. That is shown this diagram. And this can be split up into three components are there for the friction torque. And that friction torque, first component is called static friction or TS or stiction it's also called. That is the friction at the zero speed. In order for the drive to start, the motor torque should be at least exceed the stiction or this static friction, since TS is present only at the standstill. Therefore, during the dynamic operation, stiction is absent. Only during the starting period, that stiction or that's called the static friction will be present. Therefore, one component of friction is called static friction TS. That is actually we can split into that, and it is not taken into account in the dynamic analysis. Will be neglecting TS because that will be present only during the starting. Therefore, static friction or that's called stiction. That's the one part of the friction torque. Components of load torque. Continuing, in the previous slide I explained static friction stiction. That is this one. In this case, these were representing a TS. This one is representing TS. That will be present only during the starting. Second is called viscous friction. That is TV. That is a viscous friction. That is what is shown in the linear variation. This viscous friction is, that is friction torque which varies linearly with the speed is called viscous friction and is given by TV equal to a constant B into omega m. That is viscous friction is linearly related to the speed of the motor. That is, this is the viscous friction TV. Therefore, TS is this one, TV is this one. One more is the part of the friction, that is what we call it as Coulomb friction, TC. Coulomb friction torque which is independent of the speed is called Coulomb friction. That is independent of, it's a constant one. It is independent of this one, that is what is called the Coulomb friction. Therefore, sum of these one, that is static friction plus viscous friction plus Coulomb friction or TS plus TF plus TC, that is what we this one. Actually, this diagram, this is the split up part of these different frictions. This is a combining all this one, static friction, viscous friction and Coulomb friction. If you add up all this one, then you will be getting, this is the total friction versus omega m. Therefore, these are the different components of frictional torque. Second part of the load torque is called windage torque. That's also represented by TW. When a motor runs, wind generates a torque opposing the motor, which is known as windage torque, and it is given as TW equal to a constant C into omega m square. It is proportional square of the speed. And the third part of that torque, that is called torque T capital L. It is the torque required to do the useful mechanical work. That is, nature of this torque depends on particular application. It may be constant or it may be depending upon the speed, may be linearly varying, it is inversely varying, or it is a square of the speed, can be different things. That is the part of the torque that is producing the mechanical output work. Therefore, the load torque can be have three components. One we call the friction torque. Itself it has three components. We have already seen. Second part is called windage torque. Third part is called T capital, that is producing the useful mechanical output power. Therefore, the load torque can be represented as T capital L, that is this one, plus B omega M, that is the viscous friction, plus Coulomb friction. We are neglecting that stiction, or TS is being neglected. That's very small. That is why TS is neglected here. Then TC plus this one, windage torque C into omega M square. This is the total load T small l load torque. Because TC plus C omega M square, that is actually will be very less. Actually, this symbol is very less compared to B omega M. That is why this equation can be now reduced to load torque equal to TL small l equal to T capital L plus B omega M. Torque produced by the motor is already we derived equation T minus TL equal to J d omega M dt, or the torque electromagnetic torque produced by the motor equal to load torque TL plus J d omega M by dt. Substituting this value of TL in this one, then equation the electromagnetic torque produced is equal to T capital L plus B omega M by dt plus J d omega M by dt. It's a first order equation relating the electromagnetic torque produced by the motor, the torque component which is producing the mechanical output, and B omega M, this calls the viscous frictional torque. Therefore, this is the equation relating all this. The load torque can be classified in two types, that is active load torque and passive load torque. This is another method of classifying the load torque. Active load torque and passive load torque. Load torque which has the capacity to drive the motor under equilibrium condition are called active load torque. As an example, torque due to the gravitational force, torque due to the tension, torque due to the compression. In this, load torque retains their sign when the direction of the rotation of the drives changes. These torques are called active load torque. And load torque which always opposes the motion of and change their sign on reversal of the motion are called passive load torque. Examples: torque due to the friction, torque due to the windage, etc. These are called passive torque. This is called passive load torque, and these are called active load torque. That's one method of classifying the load torque. Another method of classifying the load torque: active load torque and passive load torque. Previous slides we have seen different components of the load torque. Now let us see the characteristics of different types of load torque. Speed torque characteristics, because characteristic is represented by the speed torque characteristics of the load torque. Now first one is called constant load torque, that is TL equal to a constant K. That is, most of the machine that have mechanical nature of the work like shaping, cutting, shearing, grinding, all these requires constant torque irrespective of the speed. Means that whatever be the speed, torque should be same. Therefore, this is the characteristics of the load torque that is demanding for these type of application. That's what I'm telling. What is the type of the application that will decide the requirement of the load torque versus load torque speed characteristics. Therefore, this is the one method, one type constant torque type of load, TL equal to a constant K. Second is called load torque is proportional to the speed. That is, separately excited DC generator connected to a constant resistance load has the speed torque characteristics given by load torque equal to a constant K into omega M. It's linearly related. Therefore, load torque is directly proportional to the omega M. That is another type of load torque characteristics. That is, the load torque is proportional to the speed. That is second type. Continuing the characteristics of different types of load torque, speed torque characteristics. We have already seen the two types. The third one is called torque proportional to the square of the speed. That is, Fan, no, fans, compressors, centrifugal pumps, etc. is having a characteristics like this one, and it is proportional to the square of the speed. That is represented for different applications, like this one. TL is proportional to the square of omega m square. It's not linear, it's a square of omega m square. This is for the high speed hoist, viscous friction and windage, and windage is there. That is high speed hoist, and this is the characteristic for torque versus omega m. And here the traction type of load. Traction type of load, this is the load characteristics. Therefore, load characteristics decided by the type of the load what you are using. Therefore, in this case, torque is proportional to the square of the speed. That's a third type of load. Therefore, that is for this type of application it is required. The last one is called torque is inversely proportional to the speed. Torque is inversely proportional to this one. That is actually here again. Traction load is actually coming in the during this is the inverse characteristics. In this case only non-linear, but here traction is coming in this torque is inversely proportional to speed. That is here inverse characteristics. But inverse characteristics, one beauty is that T into omega m will be constant. That is the product T, the load torque is inversely proportional to omega m, or load torque into omega m will be a constant, or T into omega m is constant. TL into omega m is constant means that power is constant. It is a constant power at all speed. For this type of characteristics, either traction purpose or this type of characteristics having the inverse characteristics between torque as well as omega m, constant power is there. That is, power is a constant power at all speeds. Example that is used in paper mills, etc. Therefore, these are the different types of loads. In first one, what we are seeing, torque is independent of the speed. Second, we are seeing torque is directly proportional to the speed. Third, we have seen torque is proportional to the square of the speed. Then fourth one, we have seen torque is inversely proportional to the speed. That these are the different types of load used in the industries and household applications.